Hello everyone and welcome to We Meet at EMC Digital Days. My name is Lisa Richter and I will moderate this presentation. We are very pleased that you take the time to participate in our virtual conference. Sorry for the delay. Hopefully we can start now without technical problems. And the topic of this presentation is magnetic materials, external solutions to reduce EMI without redesigning. Our speaker is Adrian Suarez from University of Valencia. He will hold a presentation and will answer your questions. So before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentations, but nevertheless, you have the opportunity to ask questions at any time via the chat function. You will find the chat function in the control panel. So this presentation will be about 45 minutes long, and the chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all of your questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will receive the link to the presentation in the next few days, and yes, the recording will be available at our website shortly. Now I will hand over to our speaker, Adrian, and I wish you an exciting presentation.
Hello, welcome to the presentation Magnetic Materials, External Solutions to Reduce EMI without Redesigning. My name is Adrian Suarez and I am Research Engineer of the Catedra EMC. Catedra EMC is a wide and long-term academic collaboration between the company Würth Elektronik and the University of Valencia. We reaches several areas of knowledge related to EMC, such as teaching and dissemination of science, technology and culture, research and innovation, and also training and talent attraction tasks. In this presentation, we are going to divide it into two parts. We have the first part that is focused on the electromagnetic shielding techniques based on magnetic materials, and the second part is related to the selection or the parameters of cable ferrites to reduce EMI in cables. So the trend of developing smaller electronic devices with more features and better features is increasing the problems caused by electromagnetic interferences. These design requirements may result in the next features in our designs. For example, we want to have a reduced PCB with reduced size, so we have to carry out a higher integration of the components. We also want to miniaturize and reduce the weight of our device and the housing. We use higher switching frequencies in power converters and data rates higher in communications, and we also want the possibility of our devices connected through wired or wireless communication with others. So, due to these requirements or difficulties that appear in the design, it's important to carry out the EMC engineering from the point of view of the system approach, considering EMC throughout the design process to prevent possible EMI problems that could degrade the device performance. Adopting a specific solution as early as possible in the design stage to meet the EMC requirements is essential to reduce the penalties in cost, time to market, and performance of our device. However, it is not always possible to predict EMI problems during the design stage because it's difficult to consider the real behavior of the final system that we are going to design. So when EMI problems appear, it's recommended to use a strategy where the designer can identify the following elements: the source or the EMI transmitter, also the propagation path of EMI, and the receivers of these interferences, or the victim that is affected by these interferences. So it's recommended try to suppress EMI at the source part whenever it's possible, rather than increasing the immunity in the victim circuit, because a simple EMI source could find multiple propagation paths and affecting to several victims. So it's better to act on the source. An interesting technique used to reduce EMI problems is the use of electromagnetic shielding products. These shielding products can be used to contain the electromagnetic fields generated by an EMI source, reducing its emission, or the other strategy is protecting a sensitive part of our circuit. An innovative technique to solve complex EMI problems is the use of shielding flexible sheets based on magnetic materials. We can find two kinds of solutions based on these magnetic flexible materials. One is the flexible absorber sheets or noise suppression sheets that consist of a composite material with magnetic particles embedded in a polymer. And also we have the flexible sintered ferrite sheets that is composed of pre-cracked thin ferrite plates placed between a layer of adhesive tape and a PET cover layer. This magnetic material have a property which allows them to influence the magnetic field in its environment, and this is the permeability, that the relative permeability is the parameter that defines it. This magnetic material have a greater permeability to magnetic field than the surroundings, and thus concentrate better the magnetic field lines, as we can observe in the figure. By separating the relative permeability into its complex form, we can obtain the real component that provides the reflection part or the inductive part, and also the imaginary component or the absorption or resistive part. Depending on the application, it's possible to choose a material that absorbs emission in a certain frequency region, or reflect or to concentrate the magnetic flux. For example, in this case, we have a material with a high inductive part in the low frequency region, and we have that the resistive part starts from about 3-4 megahertz. So, depending on our application, we maybe need a material that provides a higher inductive part or a higher resistive part. Besides the relative permeability, other factors that defines the performance of magnetic sheets are the sheet thickness, the size and geometry of the sheet, the kind of adhesive, and also the distance between the sheet and the EMI source that we want to shield. In order to analyze the response or the performance of these shielding solutions in different kind of applications, it sometimes could be better to obtain a real approach through some experimental characterization methods. Thereby, it's possible to analyze how the shielding, a specific shielding, is able to reduce EMI problems in a certain problem. For example, here we have an EM shielding technique based on reducing the transmission line problems. In this case, we have a PCB with several parallel lines that are connected to an integrated circuit that interconnect it with an external PCB or device. And in this case, we can observe that we have high frequency interferences that are coupling between lines or conducted, and in this case, placing the flexible absorber sheet on these lines, it could be interesting to apply a low pass filter, reducing the high frequency components with this material. For example, here we have a graph in which we can see the performance of a flexible absorber sheet. In this case, is the 324 material of Würth Elektronik, and we can compare its performance depending on the sheet thickness. We are representing a sheet thickness from 0.1 millimeters to 1 millimeter. Another problem that we can find in our designs is related to the magnetic decoupling, because it's a common problem in electronic system which holds some PCBs or devices with space limits that contain very close electronic circuits. And it is possible to protect, for example, on the left we can see that we have a PCB that has a source, EMI source, a victim circuit, but we can apply a shielding on the source and we can protect the victim. Or on the right, when we have two PCBs and the bottom PCB is affecting to the top PCB, so we can use this kind of shielding in order to protect the victim. Here we have a demo in which we can observe how a flexible absorber sheet with different thicknesses is able to reduce EMI in the high frequency region. So we have here the EMI sniffer, that it's a tool that allows us to measure the interferences emitted by a spiral antenna, as we can see in the image, and we are going to place on this antenna different sheet thicknesses of high permeability flexible absorber sheet, and we are going to evaluate how it works.
Hi, I'm Andrea, and with this video I want to show you the effectivity of Würth Elektronik flexible absorber sheets. We are going to observe the performance between 4 different sheets based on the same material, the 3441, but with different thickness: 0.05 mm, 0.1, 0.3, and 0.5 mm. When we have an element acting as a noise source, it is continually emitting interferences that can be coupled to nearby circuits, either on the same PCB or on a PCB that is placed on the top of it. This problem is known as magnetic decoupling, and with this demo I want to show you how the flexible absorber sheets can reduce this kind of problems. Here we have the setup. First we have the noise source, which is connected to high frequency square signal and is continually emitting, and then we have the near field probe to measure the magnetic field. On the other hand, we have the sniffer that acts as EMC scanner that shows the field intensity measured by the near field probe. And of course, all the flexible absorber sheets with the 4 different thickness to compare the effect of placing them over the noise source. The sniffer has 8 LEDs. The first 3 are green, then we have 3 more amber LEDs, and the 2 last in red. In this way, we can observe the level of the measured power in a very visual way. The power range is from -18 dBm to 10 dBm, so each LED corresponds to 4 dBm. We can observe that without placing any solution, we have the maximum power level with the 8 LEDs. If we go with the smallest thickness, we can observe that 1 LED is off, which means that we have around 4 dBm less field because the sheet is absorbing the magnetic field. Switching the sheet, if we go with the next higher thickness, the 0.1 mm, we can see how another 2 LEDs are switched off. And the same occurs with the 0.3 mm sheet. And if we put a 0.5 mm sheet, which is the most thicker one, we only have 2 green LEDs switched on. That means the flexible absorber sheet is absorbing almost everything. We have another solution to the same problem. These are the shielding cabinets, and we can see how much level field is absorbed. And why we are using magnetic shielding and not the cabinets? It's just because the shielding cabinet needs a specific footprint to be able to use them, and then a redesign of the PCB, which is not necessary with the flexible absorber sheets. And with all this, we have seen a good alternative to reduce EMC problems caused by magnetic decoupling without the need for redesign our system.
Okay, another problem that we can observe, for example, if we have a near-field communication system, is that when we have a close conductive surface close to our antenna transmitter, maybe we can observe how the communication distance is reduced, or maybe we have some problems with the communication between the transmitter and the tag of the receiver. This is due to we are generating eddy currents in the close or in the near conductive surface that it's generating an opposite magnetic field that is reducing the total magnetic field generated by the transmitter antenna. So if we have this kind of problems, one solution would be to shield this transmitter antenna by placing a ferrite sheet under it. So in this case we are shielding the antenna from the conductive surface through a ferrite sheet, and in this case we are concentrating the magnetic flux in the upper area of the antenna in order to detect the tag. To do this, it's very important to select the right material, because in this case we need a material that provides us a high inductive part in the frequency, in the communication frequency, at the same time that provides a low absorption or resistive part in this frequency. So in this figure, in the graph, we can observe a material that can provide this performance. Here we have a simulation in which we have the original antenna of a RFID antenna that we have simulated, and we can observe that it has a significant emission on the top and on the bottom of the antenna. But when we place a metal surface under the antenna in the second figure, we can observe that the behavior or the performance has been reduced due to the magnetic field is absorbed or is attenuated by this metal sheet. At the bottom of this slide, we can observe the simulation results obtained when we introduce the shielding, in this case a ferrite sintered flexible sheet between the metal sheet and the antenna. And in the first figure, we can observe that we have recovered the original magnetic field, but we have at the same time that we have shielding the antenna against the effect of the metal sheet. In the other figures, we can observe that we are able to recover this magnetic field, but not has a significant response as the thinner ferrite sheet, and this is due to, with the thinner ferrite sheet, we are retuning the antenna to the original frequency, whereas with the other thicker sheets of the ferrite sheet, we are moving it to lower frequencies than the desired, and we are recovering the field, but not exactly the original field. Okay, here we have a demonstration in which we can observe this problem related to have a metal sheet or a battery under the near field communication antenna, and in this case we are going to use a high permeability flexible sintered ferrite sheet in order to try to solve this kind of problem.
With the RFID systems, we have a problem when a metal surface is behind the electronic devices. In this demo, we use the ferrite sheet provided by Würth Elektronik to solve this problem. First, we are going to use this commercial device. In this board, the LED turns on when the tag is placed on the top of the antenna. If the metal sheet is placed behind the antenna, we can lose the connection. But if we place the ferrite sheet, we can recover all the connection. Now I'm going to show how the distance is reduced by using this demo toolkit that has been developed by the Catedra EMC here in Universitat de Valencia. This tool allows us to measure the distance from the transmitter antenna to the tag in the different situations. If we place the RFID tag over the antenna and we move, we can detect the maximum distance of the connection systems. As we can observe in the disk screen, this distance is about 60 millimeters. Now, if we place a metal sheet under the transmitter, we can see how the communication system is reduced and even losing the communication. However, if we introduce the ferrite sheet between the antenna and the metal sheet, we get the connection back about 40 millimeters. Now, instead of the metal sheet, we will use a battery, and we can see that the connection is not lost, but the detection distance is reduced higher than 20 millimeters. And if we place the ferrite sheet, we recover to 40 millimeters, higher than 50. In conclusion, this ferrite sheet makes it possible to solve an EMI problem with an external solution that not need a redesign of the electronic circuit.
Okay, now we are going to focus on the second part of this presentation that is related to cable ferrites. And first, we can say that the use of cable ferrites is one of the most used techniques for reducing interferences in cables. Due to this EMI suppressor provides a selective attenuation of undesired interference emissions that the designer want to suppress, and it does not affect the intended signal if the cable ferrite is properly selected. Thereby, this component is widely used to filter EMI in power cables to reduce high frequency oscillation generated by switching transients or parasitic resonance within a circuit, and also to reduce EMI in peripheral cables of electronic devices such as multi-conductor USBs or video cables. The advantage of using cable ferrite is that it does not involve redesign the electronics or the mechanical of our device. This is an important advantage because determining in the testing stage which is the EMI source may not be simple. On the other hand, the drawbacks are that we are adding an extra component in our system, so we can increase the size, weight and cost of it. So we have to optimize our selection if we have to use a cable ferrite in order to determine which material best solves the problem in our design and select the cable ferrite with the lowest weight, dimension and cost. So this is a balance between the advantages and the drawbacks. We have on the one hand the conventional materials used to manufacture cable ferrites. In this case, we want to highlight the manganese zinc that is sometimes focused on from hundreds of kilohertz to some megahertz, and on the other hand, we have the nickel zinc composition that is more focused on the high frequency region from tens of megahertz up to several hundreds of megahertz. The manufacturing process is based on the raw material that is mixed and precalcinated. After this, we carry out a milling, and the milling material is granulated, pressed and sintered, and finally a quieting layer is applied in order to obtain the final sample form. On the other hand, we have another innovative material that is based on nanocrystalline structures that is based on a different manufacturing process, as we can observe in this image. In this case, we obtain an amorphous metal ribbon that is an alloy, and we obtain the nanocrystalline structure. In this case, we roll this amorphous metal ribbon in order to obtain the final core that we can observe in blue. This material, one of the most interesting features of the material is that it provides a very high initial permeability. Here we can observe a graph with the relative permeability of the three different materials that we have explained in the last slides, and we have the nanocrystalline in red, manganese zinc in black, and in gray we have a nickel zinc. We can observe that manganese zinc is a very interesting solution to the low frequency region, whereas nickel zinc have a better response in the high frequency region. And nanocrystalline is the best solution for the ultra low frequency region, and after that have a similar behavior than manganese zinc and nickel zinc in the middle frequency region, but is reduced in the high frequency region. We can relate the permeability of the material composition that we have analyzed, and we can try to understand it from the point of view of the impedance, because we can obtain the impedance from the dimensional parameters of the sample that we want to analyze. In this case, if we analyze the impedance graph, we can observe that we should select our cable ferrite in order to provide the maximum impedance in that in those frequencies in which we can have the interferences. It's important to know that the equivalent circuit model of cable ferrite is based on an inductive part that represents usually the low frequency region. Also, we have the resistive part that provides the maximum impedance of the impedance versus frequency graph. And also we have an parasitic element that is the capacitance that appear in the high frequency region, and where it's important not select this material in this frequency region. It's better in the blue or in the green regions. Here we have a graph related to the impedance provided by samples based on nanocrystalline, manganese zinc, and nickel zinc with similar dimensions. Here we can observe that nanocrystalline is the best solution in the ultra low frequency region, whereas around 1, 2, 3 MHz manganese zinc represents the solution with higher impedance. In the middle region, nanocrystalline provides the most significant impedance, whereas in the high frequency region we can see how nickel zinc is providing the best response, the higher impedance. And one of the questions that we can have is if it's better to use more turns in one ferrite, or it's better to use more ferrites. Here we have two formulas that show that if we want to increase the impedance at the same time that we don't want to increase the cost, it's better to use only one component and increase the number of turns. But we have to consider that as we increase this number of turns, we are decreasing the self-resonant frequency. So we have shifting the maximum impedance value, or the frequency of this maximum impedance value, to lower frequencies. On the other hand, we can introduce two ferrites in series, for example, and we are adding the impedance that we can't obtain. So usually I think it's most interesting to increase the number of turns. Here we have a slide that shows us how it's possible to determine the impedance from the dimensional parameter that offers the cable ferrite. This is the height or the length of our cable ferrite, and also the inner and outer diameters, because with these parameters and the relative permeability of the material that we are using, it's possible to determine the impedance. From this formula, we can obtain several conclusions or main ideas that are important in order to select certain cable ferrite. Because considering these parameters to maximize the impedance provided by the cable ferrite, it's interesting to select the maximum OD ID ratio, the maximum height, while the ID is as tight as possible to the cable diameter. Okay, but nevertheless, the increase of the dimension is usually proportional to the weight, the volume, and cost. Hence, a balance between these three features and performance should be carried out. Thereby, it should be taken into account that the impedance is proportional to the natural logarithm, as we can observe in the formula. This logarithm is the ratio of the outer and inner diameters, and also the impedance is proportional or directly proportional to the height. Even though the height is directly proportional to the impedance, but the natural logarithm provides an attenuation factor when the ID is lower than 2.7 times the OD. So that it's crucial not selecting thin cores. For instance, if we select an OD-ID ratios of 2.0, we are applying an attenuation of about 30% in the response of the impedance of our cable ferrite. So it's important not selecting thin cores. Therefore, not always the cable ferrite with higher volume provides the best performance. For example, here we have in the table some cable ferrites with different volumes, and all of them are able to provide a similar impedance response as we can observe in the graph. In the case of red and yellow, we can observe that the red one has a higher volume than the yellow one. But in the graph, we can observe that their impedances are quite similar. On the other hand, it's interesting to analyze the insertion loss parameter, because in the datasets we usually can find the impedance of the cable ferrite, but sometimes it's interesting to know the attenuation in terms of dBs that is able to provide this component. There is a method that we can apply in order to obtain this attenuation, and this is by knowing the impedance of the A system in which we are going to connect our cable, and also the input impedance of the B system, the other part of the cable. So by knowing the two system impedances, we are able to apply this formula, and by introducing the impedance of our cable ferrite, it's possible to obtain the attenuation on insertion loss. Sometimes it's difficult to determine the impedance of the system with EMI problems. However, depending on the signal that flows through the cable, it's possible to estimate this value. We can to do an approach. For example, we have here 4 items that we can observe. For example, for ground surface, we can estimate an impedance of about 1 or 2 volts or 2 ohms, or if we have data lines, we can estimate that we have in the A system 50 ohms and in the B system 50 ohms. Okay, so this could be used as an approach. And finally, I am going to carry out a demonstration in which we are going to analyze different cable ferrites from the point of view of the insertion loss. So we are going to use a setup in which we introduce a cable ferrite, and we are able to observe the attenuation provided depending on the frequency and the materials. Now we are going to start with the live demo, and we are going to use in this case a network analyzer device, because this equipment allows us to measure the S21 parameter. The S21 parameter is related to the energy that arrives to this port 2 from the port 1. So which amount of energy is received in the port 2 with respect the emitted by the port 1. So a simple test that we can do is connecting the port 2 directly to the port 1 in order to observe the behavior So we place here in the port 2 and the port 1, we can see that we have a flat response centered in 0 dBs, and this is due to we are connecting directly port 2 with the port 1. So this setup is going to be used to characterize the behavior of the different cable ferrites, because now if I change this cable that it's shielded and connected to the reference of the equipment, and we use this other setup, okay, that only connects the port 1 and the port 2 through the signal line, we can observe that in this case we have not the flat response because it's not perfect. This line is not shielded, so it has some losses, but we need that having a flat response in order to analyze better the behavior or the ferrites that we are going to evaluate. So I am going to calibrate the equipment in order to obtain a flat response. So we have cancelled the response and we have the flat response, and now we are going to use different cable ferrites. In this case we have here some codes based on manganese zinc, nickel zinc and nanocrystalline, and we are going to observe the frequency range in which they are most effective. So now if we place the manganese zinc, we can observe that we have the higher attenuation in the low frequency region. For example, here at 1.5 MHz we are obtaining 7.8 dBs of attenuation, and we can observe that in the high frequency region this kind of material is not providing a significant response or significant attenuation. But if we change manganese zinc by nickel zinc, in this case nickel zinc has a lower initial permeability, in this case is a 600 initial permeability composition, we can observe that we have moved the frequency range with attenuation to higher frequencies, and we have, for example, here in 67 MHz we have 7.2 dB of attenuation, for example, and we can see that in the low frequency region the solution is not providing attenuation. For example, here at 1 MHz we have 0.1 or 0.2 dBs. Now if we evaluate the nanocrystalline response, we can observe that in this case in the ultra low frequency region this sample is providing attenuation. For example, here at 1 MHz is providing 5.8 dBs, or here at 100 kHz is providing 2.4 dBs. And also in the middle frequency region, for example, here at 30 MHz is providing 8.2 dBs of insertion loss or attenuation. So it's a wideband solution because it's able to provide attenuation both in the low frequency and in the middle frequency region. In this case we are evaluating these ferrites considering that our system has an input impedance, or the A system could be represented by port 1 and the output impedance is 50 ohms, and the input impedance, this port 2 represents the B system, is an impedance of 50 ohms. So the total impedance that in the system is 100 ohms, and we have to introduce cable ferrite that introduces a higher impedance than the system in order to have these attenuations. Okay, and now we are going to evaluate an snap ferrite. Sorry, I'm going to disconnect here. And we are going to use, I'm going to connect it, this kind of snap ferrite that can be applied without disconnecting the cable, and I am going to place it in our line, and we can observe that we have a quite similar response than the nickel zinc core, because this snap ferrite is based on the same material than the the last nickel zinc sample, and we can observe the same frequency region, and we have quite similar attenuation at about 63 megahertz. We have 8.2 dBs. What happens if we increase the number of turns? We have here only one turn, but I have here another setup with 2 turns. We are going to modify it. Okay. And now we are going to connect it. Okay. And we have observed that we have the resonant frequency in a similar frequency region, maybe a bit lower due to the increase of the turns, and we can observe an attenuation of about 17 dBs, 0.3. So it's very interesting this technique of increasing the number of turns. And now if we increase it to 3 turns, we can observe also this increase. So we have here 3 turns, the same component, okay, and we can observe that we have the resonant frequency about 58 megahertz, and we have obtained an attenuation of 25 dBs. So very interesting value of attenuation. And another situation that we can evaluate with this setup is the use of different dimensions of cable ferrites. As we can observe during the presentation, we can compare this sample with these 2 others, and we can try to understand why happened this, because if I place this cable ferrite here, this is a nickel zinc cable ferrite, as we can observe in the representation of the equipment, we obtain a maximum response of about 8.6 dBs at 61 megahertz. But if I try with this other smaller sample based on the same material, on the nickel zinc composition, we can observe that we obtain a similar response. We obtain at 61 megahertz an attenuation of 8.1 dBs. And what happened is because this higher sample, this bigger sample, has the inner diameter, and or the relation between the inner and outer diameter is lower than in the case of the smaller sample, because here the inner diameter is close to the cable, and we have here a thicker material than this one. But if I try the other small cable ferrite, in this case we have the inner diameter separated by the cable. In this case we can observe that we have a lower performance because here at 61 megahertz we obtain 4.6 dBs instead of the 8 provided by this and this. So with this we can understand that the volume does not indicate the performance of our cable ferrite, because we have to consider the inner and outer ratio and also the height or the length of the cable ferrite, not only the volume. Okay, with this we have finished this presentation, and I want to conclude that with this presentation we have seen that the use of magnetic materials to reduce EMI problems through shielding solution or cable ferrite components could be an interesting solution when we have problems, particularly if we are in the testing stage. So I think it's a very interesting solution, and I hope that you can consider them in your future designs. Thank you for your attention.